Let's go. So hopefully we're going to write with 5C1, 5C2. This is just a very short extension on it. The questions get a little bit more complex, but same skills, same techniques. We're still focusing on kinematics, right? So the example problem we've got here, we'll just leap straight into it, is we have an acceleration function. We have a solar sail accelerates according to this function, where t is time in seconds. And so, if you're doing physics, a solar sail is something that constantly accelerates, right? Photons hit it, transfer momentum, and it keeps getting faster and faster and faster. So this is the acceleration function. What's it asked us to do? Part A, find the velocity function given the initial velocity is 0. Well, the velocity function is equal to the integral of the acceleration function, right? If you differentiate velocity, you get the acceleration function. Therefore, if you integrate acceleration, you'll get the velocity function. So we've got to perform the integral of this function. And straight away, I'm expressing it at the top with the power of n. The 100 is just going to hang out the front, right? Because it's a number multiplying it. And then we have t plus 2 to the power of minus 2. So it's ax plus b to the power of n. So it's 1 on ax plus b to the power of n plus 1 on top of n plus 1. Alright, and then plus c, so we'll just process this a bit. So what are we going to have? We're going to have 100 times t plus 2 to the minus 1 on top of minus 1. Minus 100 on top of t plus 2 plus c. So that's all good. And then we know that the initial velocity is 0. So that means when time is 0, the velocity is 0. V of 0 equals 0. So we'll plug that in. So we're going to have c is 50. Alright, so that means our velocity function is minus 100 on top of t plus 2 plus 50. So that's going to tell us the velocity for any value of t, right? Part B. So what do we do there? All we're doing is we're recognizing velocity is the integral of acceleration, and then we're finding a particular circumstance given some extra detail about the initial velocity. On to part B. Find the integral from 0 to 300 of v of t. So that means the integral from 0 to 300 of this function, right? Minus 100 on t plus 2 plus 50 with regards to t. Okay, so let's break it into parts, I think. Let's focus on this part. I'm going to write that as minus 100 multiplied by 1 on top of t plus 2. And then this one we'll just write as the integral from 0 to 350. Alright. Now the reason I've written it like this is perhaps that can help you see what we're integrating here. We have 1 on ax plus b. And so that goes to 1 on a ln of ax plus b. Alright, so the minus 100 staying out the front, we have 1 on a ln of ax plus b. I'll put modulus there, you don't have to. So that's from 0 to 300. And then here, 50t from 0 to 300. You can include it in the same thing if you want. I just split it to make the point about what that integrates to. Okay, so plugging all that in, we'll have minus 100 ln of 302. Take ln of 2. Plus 50 times 300. Alright, what's this? Minus 100 ln of 151. So that's the answer exactly right. Let's convert it to 3 significant figures. Another way we can check our answer is to plug this in and then put the integral statement in and make sure they're the same. I'm just going to type this in. I think it might be a little bit faster. 15,000 take 100 ln 151. I've got 14,498. Alright, so I've written 5 figures there. And so this might be a good opportunity for us to talk about rounding, right? If it says, 14,498.2. So if it says to the nearest meter, alright, we'd round the 2 downwards. If it says to the nearest 3 significant figures, these are the first 3 figures. So the 9 is going to round up. So we've got 14,500 meters. Alright. State its significance. Okay, so the integral under the area under the velocity curve is distance travelled. All right, it's the displacement travelled. So this might be a good opportunity for me to explain that. The integral from a to b of a velocity function, okay, is always displacement. Okay, it's always displacement, and it is distance as well, provided it doesn't change direction. Okay? Because distance and displacement are the same thing if it doesn't change direction, right? So it's always displacement, area under the velocity curve, but it will be distance as well if it doesn't change direction. And if you look at this velocity function, all right, it's going to look something like this, I think. Something like that anyway, but it's always positive. So the velocity is not changing direction because you never have negative velocity. So you can say 14,500 meters, that's how far it's travelled in the first 300 seconds, in the first 5 minutes, right? So the solar sail travels 14,500 meters in the first 300 seconds. Alright, so that's the distance and the displacement because it doesn't change direction. That's how far it's traveled. Alright, so all we're doing in this exercise, I think the only significant difference is